All right, so today we're talking 6.2, multiplying radicals. So multiplying radicals is a lot like multiplying exponents, where they have to have the same index. And when they do this, when we have the same index, we're looking at multiplying the radicands together and leaving the index alone. So here we have an example of the square root of, or the cube root of 6 times the square root of 2. All right, and so it says, can you simplify the product of the radical expression? Explain. The answer here is no. They have different indexes. So if we look here, we've got cube root, square root. Not the same, so we're not doing it. But in the next one down, we've got the cube root of -4 and the cube root of 2. This time the indexes are the same, so we would have the cube root of essentially whatever -4 times 2 is. And in this case, that would give us the cube root of -8. The cube root of -8 is just going to be -2. Here we've got more practice doing the same thing. You'll notice here in the first one, we've got the 4th root of 7, the 5th root of 7. They're different indexes. We're not doing it. And then from there, in B, we've got the 5th root of -5 and the 5th root of -2. So essentially, we've got the 5th root of -5 times -2, which in this case would be the 5th root of 10. And that's how we're going to leave this. Here it says, what is the simplest form of 3, or the cube root of 54x to the 5th? So now we're looking at simplifying radical expressions where it's not necessarily a perfect cube, perfect 4th root, things like that, where we're going to have to manipulate the expressions a little bit. So ideally, we're taking the cube root of 54, which there isn't a perfect cube root of 54, but we also have the cube root of x to the 5th. So we're going to break this apart. Let's just start with the 54. In terms of cube roots, I know that 54 doesn't have a perfect cube root, but what I can do is break this apart. This can be broken apart into the cube root of 27 times the cube root of 2. Let me write that a little bigger. It's hard to see. The cube root of 27 in this case is just 3. And then this would just be the cube root of 2 still. It remains. Here we talked about this before, that the exponents or the powers on the variables essentially are getting divided by your index. Well, in this case, 5 does not divide evenly by 3. So what I want to do is I want to separate this into x to the 3rd times the cube root, I guess I can put it into the same radical, times x squared. So these two will be just fine. The cube root of x to the 3rd will be just fine. It'll come out as just x. But we're leaving behind the cube root of x squared. And so now what we need to do is bring all of this back together. So we've got 3x and then the cube root of 2x squared. All right, so we'll do the same thing the next one. We've got the cube root of 128, x to the 7th. So in this case, I know that we're essentially taking the cube root of everything. I know that 128 can be broken apart into 64 and 2. 64 is a perfect cube. And then for the x's, I can do x to the 6th and x to the 1st. And so ideally, I'll be able to cube root this and this. And so doing so, I'm pulling out the 4x squared, and I'm leaving behind these because they cannot be taken the cube root of. So, so that becomes 2x. Now we're talking about multiplying radicals. And we looked at this in the previous section. Multiplying means we're going to multiply as long as they have the same index, and they do. They're both square roots, so essentially they're both the 2. And then so we're going to multiply the items underneath together. So in this case, we will take 72 times 10 which is 720. And then we'll go ahead and multiply the x to the third with the x to the first, which becomes x to the fourth. And then y squared and y to the third, that's going to be y to the fifth. And keep in mind our index in this case is a 2, so we're trying to reduce this. Now we have to simplify this. I know that 720 is not a perfect square, but it can be broken apart into 144, and in this case, 5. Then this is a perfect square, so we can just take the square root of x to the fourth, that's fine. But for y to the fifth, we're going to have y to the fourth times y to the first. And so the things that can get square rooted are the 144, which is going to become 12, the x to the fourth, that's x squared, and the y to the fourth, which is y squared. These items will remain underneath the radical. So we're going to have 12 x squared, y squared, square root of 5y. All right, we're doing the same thing here again. But this time, we could actually, before multiplying these things together, we could essentially reduce the actual expressions first, since they have the same index, before we bring them together, and see if we like that method better. So you could do them separately, or you could just combine them like before. So ultimately, it's up to you. I think doing them separately in this case actually ends up with a couple more steps, but the numbers are easier to deal with. I'm actually just going to go ahead and do the same way we did before. Since they have the same index, we're going to multiply the 45 and 35. So 45 times 35 in this case is going to give us 1,575. So it's a really big number. Then we move on, we've got the x to the fifth and the x to the first. So that's x to the sixth. And then y to the third, y to the fourth. That gives us y to the seventh. And so keep in mind we're square rooting this, so our index is 2. All right, so we'll break apart this. This might be harder to see, but in this case, I know that this breaks apart into 225 and 7. This is already a perfect square, so we're good. And here we're going to have this break apart into y to the sixth and y. So the square root of 225 is 15, so we've got 15. We cannot square root this, so we're all right. Then we've got x to the sixth square rooted becomes x to the third, y to the third, and then we can't square root the y by itself. So that and the 7 remain underneath the radical. So this becomes our simplified form. You could have separated and started, like I said before, separating these out and kind of working with it. You would have known if you broke apart the 45 to start with, you would have had 9 and 5, but the 35 doesn't get broken apart into anything that works. So you would have had 3 square root of 5 and then the square root of 35. Then you would have had to bring these two together and then break that apart. It actually adds some steps, but the numbers, like I said, are easier to deal with. So the options are yours. There are lots of ways to tackle this problem. So division problems are a lot like multiplication. As long as we have the same index, we can write the quotient of the roots as the root of the quotient. So in this case, we can combine them as long as they have the same index. So ideally, we're still looking for an opportunity where we're trying to divide where the indexes are the same. So instead of having 2 separate indexes, you can then place the entire fraction or division underneath the one index. So as we look at this first example, both of these radicals here have an index of 2. It's the square root, so we're good. So what this means is we're going to go ahead and rewrite this like this. 18x to the fifth over 2x to the third, and then we're going to square root the whole thing. This allows us to simplify underneath the radical before we try to square root anything. So like in this case, I know that 18 divided by 2 is 9. And then with the exponents piece here, I know that division means they subtract. So that means this becomes x squared. So now we're looking to take the square root of 9x squared. Well, the square root of 9 is 3. The square root of x squared is just x, so our answer is 3x. For b, we can do the same thing. They both have an index of 3, so we'll bring them together. 3, we've got 162 over 3, and then we've got y to the 5th on top and y squared on the bottom. So 162 divided by 3 is 54. And then we subtract the exponents, this becomes y to the 3rd. All of this taken to the cube root. 54 is not a perfect cube, but what I do know is you can get 27 and the cube root of 2 when you separate it. Y is a perfect cube, so it'll work, or y to the 3rd, that is. And so we simplify this. We know that this is going to be 3. We know that this is going to be y, and this does not work, so we leave it underneath the radical. So 3y and the cube root of 2. All right, here we're doing the same thing. Go ahead and pause the video, try this one on your own, and unpause it when you're ready to see the answer. All right, so another way to simplify radical expression is to rationalize the denominator. You rewrite the expression so that there's no radicals in any denominator and no denominator in any of the radicals. So the idea is to try to multiply by whatever the denominator needs in order to cancel out the radical. So in this case, if it's the square root of 2, you would need an additional square root of 2 in order to cancel it out, so you'd multiply top and bottom. If it were the cube root of 2, let's say like this, you essentially need 3 of those 2's. Well, you already have 1, so you'd have to multiply by the cube root of 2 squared in order to cancel that out, and you do that to both sets here. So that way, on the bottom, when you multiplied this together, you'd get 3, or the cube root of 2 to the 3rd, which would then just cancel out to be 2. So you're trying to essentially get rid of the radical in the denominator. All right, so let's look at some examples of this, and it'll make more sense, hopefully, as we move along. So let's just start with problem A, where we're trying to rationalize the denominator and find the simplest form of each of these. So for A, we're trying to get rid of the denominator of the square root of 2. So that means we're going to multiply the top and bottom of this problem by the square root of 2, because essentially to cancel this out, we just need another square root of 2. So since they all have the same index, we can multiply straight across. We've got the square root of 2x over, well, in this case, it'd be the square root of 4, which in this case is going to be the square root of 2x divided by over 4. Oops, sorry, the square root of 4 is 2, not 4. I knew I was making a mistake. There we go. Square root of 2x over 2. There we go, that's better. All right, same thing in B. We want to find a way to rationalize the denominator. We've got the cube root of 3, or the cube root of 2, wow, on the bottom, and we've got the cube root of x on top. So we're going to multiply both of these by, well, essentially, in order for the 2 on the bottom to come out of there, we would need 3 2's, essentially. So that means we're going to have to multiply by the cube root of 2 squared, because essentially for this to cancel out the way we want it to, we need 2 more 2's, so that way there are 3 of them being multiplied together. And then here, we're going to multiply this by the cube root of 2 squared. All the indexes are the same, so we can multiply across. We've got the cube root of 2 squared times x, which would be 4 in this case, over the cube root of essentially 2 to the 3rd power. So in this case, we could multiply that out, but we know that cube rooting this is just going to work out the way we want it to. So this is going to be 2. And then on top here, this would just be the cube root of 4x. And then last but not least, we're back to a square root problem. We're trying to cancel this out. So we look and see, what do we need to multiply by to rationalize the denominator? Well, it's going to be the square root. We need another 5, we need another x, and we need another y. So it would just be 5xy. And so we're going to multiply across to do this. So on the top, we're going to get 15x squared y to the third. On the bottom, we're going to get, and I'm going to leave it like this, 5 squared x squared y to the fourth. We can't square root 15. We can square root the x squared, so the x will come outside. We can square root part of the y to the third, so we'll get y out here, and then we're leaving behind 15y underneath. On the bottom, all of this can be square rooted, so we're going to get 5x y squared. And then the last thing we want to do is simplify as we go. And so as we simplify as we go, we should recognize that the x's here are going to cancel. This y cancels with one of the y's there. So our final answer here just becomes the square root of 15y over 5y. So here we have one more example of this type of problem. So we look and we have the cube root of 7x over the cube root of 5y squared. To rationalize our denominator, we'd have to take the cube root of 5 squared and then y, so that way we get it to cancel, and we do that to top and bottom. And so because of this, we can multiply straight across because the indexes match. So that's the cube root of 35. What is this? X. Actually, not 35. That's 5 squared. So 5 squared would be 25. So 25 times 7, that's 175. Then we've got x, and then we've got y. Over, in this case, we've got the cube root of 5 to the third, y to the third. And so now we just want to simplify as much as we can. And in this case, the top we're going to actually leave alone in this case. So we're going to get the cube root of 175xy. And on the bottom, we can take the cube root of 5 to the third, just becomes 5. Cube root of y to the third is just y. And this is our answer.